Because the FDR did not, that the wall, the switching terms came into place after FDR. It's not like you broke the wall, so now we'll all replace it.
Well, you will abandon all laws.
I don't know, he's close enough to getting his leash as it is. He starts to really he's really done. Yeah. And his son in old class will really be helpful too, right? Who the heck names their son that? That's so happy.
I'm sure they'll
Ready? Okay.
Hey, good evening, everyone. So this stuff's pretty cool today. We're doing 13.1 and 13.2. These are on vector functions. And then we'll do derivatives and integrals of vector functions. We've already written a line as a vector function, right? But that's what we're doing, but these will be different from lines. We may get a line in there, but you're going to have vector curves. So you can also call these vector curves. You can call them space curves if you want. Sometimes they're in two-dimensional space, but we're going to look at a lot of problems that are in three-dimensional space. Might even look at it with the software. We can draw them on our papers. I'll draw it on the board, but sometimes it's neat just to see it done with, something like I'll use WinPlot. We'll make these graphs. So I'm going to start with a two-dimensional vector function. And I'm just going to call it R of t. And I'm going to set it equal to, let's see, 4 square root of t and 4 minus t for the x and y components. And we're just going to go ahead and sketch this. We'll sketch this vector curve. So we'll talk about, well, how do you do that? Because of the parameter involved. This is the x-axis. That's the y-axis, and you have these t's in here. T is that parameter. And so it's the idea we got a parameter and we got our x and y variables. So how do we sketch a vector curve? One way is just to make a table. Just make a table. You got t's, you got x's, and you got y's, and you can simply make up t values and plug them in. Where's the x and the y? Right here, that's the x, and that's the y. The y. So just remember that. There's x, there's y, so when it comes down, where do I start? I don't know where to start in terms of making this sketch. I have to sketch this in the xy plane. You can simply just make a table, and you get to create t values. So how about we'll sketch this from t equals 0 to t equals 4. So, all right, 0, 1, 2, 3, 4. Now we plug these in. What's 4 times square root of 0? 0. 4 times square root of 1? 4. 4 times the square root of 2 is 4 root 2. We can look at that value. 4 times 1.4. 3. 4 times root 3. At least this is neat. What do you get there?
8.
8. What are these? Well, 4 minus 0 is 4, 3, 2, 1, and
0.
0. And then you'll notice, oh, I've got a curve. And I can just go ahead and plot these points. We'll definitely plot this one. This one's nice. And we'll definitely plot this one. This one's nice. And we'll plot this one too. All right. So I'm going to go out to, it looks like I have to get at least out to x equals 8. 1, 2, 3, 4, 5, 6, 7, 8. And for y, I only have to get up to what? 1, 2, 3, 4. 4, 8. Let me plot these. It was 0, 4. Then it was 4, 3. Then it was 8, 0. You can plot these if you want as well. But you'll notice it's curving, right? It's not a straight line. If you wonder what a straight line would have been, this would only have like 4t. No t squares, no radical t's, you get straight lines. I'll connect this curve. Now what you should do with vector curves, is put an arrow to indicate the path. The path in which t is increasing. Just put it anywhere on the curve. So which way is this thing going? That way or this way? Anywhere you want, you can just go, all right, it's going that way. That gives the direction as t increases. Of course, we can apply to more points. And you got the vector curve. There is another way to do this. This is a simple way. This works all the time, especially when it's in two-dimensional space. But there is another way where you can actually eliminate t, eliminate the parameter, and then you just have x and y, and you can make the curve, right? You'll have a curve in terms of x and y, and you sketch it like you're in a, back in a pre-calculus course. So just another way. You can't do this with all the problems, but many you can. You look at something like this, you're like, well, can I just eliminate the parameter? And you'd have to do this by substitution. So x equals 4 square root of t. Y equals what? 4 minus t. So is there a way I can substitute this into there and just get x's and y's?
Yes.
What would t equal to here?
X over 16, x squared over 16,
You could do that, or even in this case, well, if t would equal what?
4 minus 1.
Y plus 4? And where can I substitute this? Right into there?
Mhm.
And this is one way, and you got x equal to what? 4 square root of y plus 4, right?
Uh-huh.
Awesome. So I mean, it's just, but there's one way you can do is look at, hey, I got a curve now.
Wouldn't it be 1 minus?
In this case, so this would be, if I did the t, let's see, t would equal, yeah, 4, would it be 4 minus y?
Yeah.
Yeah, thank you so much. So in this case, let me rewrite that. Thank you so much. T would equal, we add t to both sides, 4 minus y, and then we would have x equal to 4 times the square root of 4 minus y. But who knows, maybe that's not so helpful to you when it comes to sketching the curve, right? You could square both sides, what would you get?
X squared,
X squared equals 16, now you just have what?
4 minus y.
You're like, oh, okay, I see. Sounds like this is part of a parabola. What would that be? 64 minus 16y. You have that relationship. So I just wanted to point that out. Sometimes you might find that easier just to eliminate the parameter. Cool. Now, these all vector curves. Can we draw some certain vectors on this thing? I'm going to start with the position vector. Can you draw the position vector at t equal to 1? Can we draw on this sketch the position vector at t equal to 1? The position vector will always start from the origin, all right? And that tip of that vector will land right on the curve. So when we're looking for r of 1, and what do you plug in here? That means you just go to the original function, you plug in a what?
1.
A 1. What would you get? Want to be these numbers?
4, 3, yeah.
4, 3. And I'm going to sketch that. Means I went over 4 and 3 what? But this is the position vector, so I'm going to label this. There it is. Give it an arrow. That's R1. I'll put an arrow on there. See how it's tip laying right on that curve? Cool. Now, it's okay to talk about it right now because we're covering both sections today. We're going to be doing derivatives. So when we look at the derivative of that r of t, which would be r prime of t, let's check that out. Let's look at the derivative of r of t. Well, the derivative of r of t would be what? R prime of t. If that's the position vector, what do you think r prime of t would be? There's a position, starts with a v.
Velocity.
Velocity. This, you can call this the velocity vector. For right now, I'll just leave it r prime of t as the derivative, but it's also called a tangent vector. So r prime of t is, you can think of it as the velocity vector, but also as the tangent vector. So when I say tangent, you know about tangent lines? You bet that vector will be tangent to this curve. Okay? So let's find r prime of t, and then we'll find r prime of 1. We'll find the tangent vector at t equal to 1. All right. How do I do these derivatives? So really, this comes into play in 13.2, but it's okay to talk about right now because we're doing vector functions. R prime of t need the tangent vector. Let's see what we get. All right, let's derive or square root of t. That's t to the 1/2. So 1/2 times 4 is
2.
2. Then you decrease this by 1.
T to this.
Derive square root of t.
Mm-hmm.
Nice. That's an easy derivative. What's that?
-1.
All right. So now after this, right underneath it, can you find the tangent vector at the value 1? So this is going to be at t equal to 1. Find the tangent vector at t equal to 1. So that'd be r prime of 1, substitute of 1, what do you get? 2 comma what?
-1.
Negative 1. And again, these are derivatives, so this is something that actually comes into play in our textbook in 13.2. These sections go together. Since we did a vector function, we can just draw some tangent vector. When I draw this, I need you to start this from the tip of your position vector. And when you draw it and sketch this vector, you'll notice it'll be tangent. So I gotta go what? 2 to the right and then 1 down. True? But I'm not drawing it from here, I'm just gonna draw it right from here. So I go 2 to the right, and I go down, run, and does that look like it's tangent?
Mm-hmm.
Too bad. And I'm gonna label this r prime of 1. You can also call it b of what? 1. It's the velocity vector. So another thing, you can call this the velocity vector. I'll put a v on there if you want. Velocity.
So the tangent vector is called velocity vector.
The velocity vector. If we're thinking of this in terms of the position of some object, right?
Okay.
And it's moving, or a particle,
Uh-huh.
or it's a bug, some bug flying, right? The velocity vector is the tangent vector. Well then, what would r double prime be if this was position?
Distance, right?
The derivative position, we got velocity. The derivative velocity is
Acceleration.
acceleration. So let's find the acceleration vector, which would be r double prime of t, right? Okay. Well, I've got that up here. Can I erase these points? Okay. Still right here. So now we're going to have to take the derivative of that. What's a prime of t? Which would be r double prime of t, right? We put 2 slashes on there. Let's see what we get. Are you ready? See, when that's 2t to the negative 1/2. You got to take a 2t to the negative 1/2 and apply the power rule. So what's negative 1/2 times 2? Negative 1 t to the negative 3/2. Okay. And what's the other component? What's the derivative of negative 1? 0. So when I just took the derivative of this, and we got the negative 1t to negative 3/2, I took the derivative of negative 1, constant 0. Can we write this again then? A of t, or r double prime of t, is negative 1 over a what?
Q 3 at 0.
Now, can you find the acceleration vector at t equal to 1? This will be at t equal to 1. Can you find the acceleration vector?
-1.
Negative 1 and 0. Acceleration vectors are funny. Sometimes they're like this, sometimes they're like this. If it's a circle, if you get a particle that's moving in a circle, which way is the acceleration vector point? Anybody know? It points inward. Very good, he knew. You can actually, if we took a vector function with a circle, you'd notice that. Where's this thing? See, it's funny? What is this? This isn't much, is it? It's going to be a little beep. So we got to move. And we also draw this from the tip. From the same point you're drawing the tangent vector. So I'm going to go what? 1 in that direction, but I won't go up.
Mm.
So I'm just from this point, just go a little bit, stop. And that's your acceleration vector. A of 1. That little guy. Good job. Hey, any questions on that? Cool, what you bet? So what if something's going like this? You'll notice like that acceleration might be like this. The tangent vector would be like this. And these two vectors would be perpendicular to each other. Cool. Alright, let's look at some vector curves that are in three-dimensional space. So I'm going to start out with this guy. R of t. I mean, when they have, I'm going to write this, but we won't sketch this. They have vector curves like this in there. And absolutely, you can sketch that, but what could you do? You could just make a what? You can make a table and just start what? Plotting points, right? So we won't sketch this. I just want to give you an example. You'll see some problems in section 13.1. They'll say, sketch the vector curve. It's in three-dimensional space. You're like, well, where do I start? You just end up what? You make some t-values. You get a sense of how this thing's going. Okay? What we're going to look at is problems where maybe we don't have to sketch so many points. So other than this, here's the one we're going to do. How about this is sine of t. This is cosine of t. And this is t. And this is the x component, and this is the y component, and this is the z component. Surely I can do what? Surely I can make a table and make up some t-values like what? 0, pi over 2, pi, 3 pi over 2. But we'd still get these little points over the place. It wouldn't help us much in terms of making a really decent sketch. So, let's at least get 1 point just to get it started. What's going on at t equals 0? Sine of 0 is 0, cosine of 0 is 1. And then this t value would be what? 0. All right, so there's 1 point on the curve. There's 1 point on the space curve. But I want you to look at something else. Let's look at relationships. So I'm going to hide this. And when you know what's the trig identity in terms of sine squared plus cosine squared is equal to?
1.
I'm going to write that down. Because that really, really helps us out with these problems. Like the sine squared of t plus the cosine squared of t is equal to 1. True?
Mm-hmm.
So if I hide this, what's the relationship on this vector curve between x and y? Don't you see a circle? Because x squared plus y squared equals 1. You all see that? Because of that trig identity. That's just an observation that we'll make. We could have plotted some points, but I don't think it would help us to make a decent curve. So like, oh, it's like this curve kind of has something like this going on between x and y. But there's also a z involved, isn't there? So if this thing's kind of circling around between x and y, what's going on with z? Well, as t increases, the z keeps what? Increasing. Do you know, Brad?
Wouldn't it be like an infinite radius disk?
And what would it do? Because remember, it is a curve. It's a curve, so it's doing this.
Keeps going around in concentric circles.
Exactly. And as t increases, it's just going to keep doing this, right? And it would center right on the z-axis. This would be a curve that just keeps circling around the z-axis. It's a curve. There's a name for it. It's called a helix. This right here, it's called a circular helix. And you and I make a sketch. Just a rough sketch and say what? Well, here's the y-axis. There's the x-axis. You might say, well, I want to plot at least 1 point. Okay, let's just plot that. Where is that? Where's 0, 1, 0? Right there. Heck, if you wanted to get another point, you could, right? But just go ahead and make a little... Make yourself a note that this is a circular helix. Anybody ever seen a slinky before?
Mm-hmm.
Yeah, there you go. Corkscrew. Corkscrew. Sometimes I think it's nice to see it with the what? With the software, so I'm just going to use WinPlot here. I'll hit the light real quick. We don't have to do this with every curve, but sometimes it is nice to see it happen. And when you can actually get this is WinPlot. Sorry, download it for free. And I'm just going to go in here. Is it picking up? Yeah, I'm just going. I'm going to type in the parametric
I think I'll
equations.
move this way.
Okay.
Yeah, that's big enough. Yeah.
Excellent. Is that okay?
Mm-hmm.
Oh, cool. Hey, so this is WinPlot. I'm just going to type in parametric equations. What was the x component? Because are the parametric equations of the vector curve. We got a what, a sine of t? All right, what's the y component? Cosine of t. And z is just a what? T. I did notice sometimes if I give this more slices here, like I let t go further out, like maybe out to like 25, it does make it look a little bit better. Then you give a little more division, and you'll see this thing. Now I'm going to just say view axes, just so you can see the x and y and z axis. And just let it swirl around. Don't let those things at the end bug you. That's just the software doing that. But I did want you to point out this thing will just keep doing what? Just all the way around being a circular helix. Cool. And if you want to tip it upside down and look inside of it, it's kind of cool, and you see the what? See what I mean? It's like, oh yeah, this thing is a circular helix. Cool? Hey, well, I'm going to close this out, and this is my next problem. And I'll write this on the board, so you can stay there. Stay there, and I'm just going to go in here and go parametric. Well, what did I have before? Sine, cosine, and t. Well, what if I put t in front of the sine? Let me close this out, sorry. On the equation, go parametric. What if I put t in front of the sine? I apologize, I want to do three-dimensional space. Equation parametric, there we go. T times sine of t. All right, and then we'll use t times cosine t. And then z is just going to be that 2. So all I'm doing here, what I want you to notice, is in this scenario, I am now putting t's in front of the sine and the cosine. So I'm just going to put a t right here. This was a circular helix, right? How would this affect our problem? I'll tell you what, it'll still be a helix, although this would be 0, 0 here. And then we'll sketch it there, but I just want you to see something. So, okay, what if we put t's in front of that? Well, it still should be a helix. Does anyone have a sense of this? Right? I love it. They're saying, very good intuition, they're saying, this will just what? As t increases, 1, 2, 3, 4, 5, what's getting thrown in front of these circles? 1, 2, 3, 4, 5. That's making the radius of the circle getting bigger and bigger and bigger. So this will be, the last one was a circular helix. We can call this like a conical helix, right? In our rough sketch, we'll look at it with the software, what should it do? It should maybe start out like this, and then the radius gets bigger, and then what? Bigger and bigger. It's like a conical helix. Cool. Hey, let's see how it looks. Again, I'll just give it a few more slices in there. Here, let's see. I'll give it maybe, here we go, 50, try 150. Maybe this will look okay. Boom, did it look all right? View the axes. Sometimes it just chops it up a little bit like that. That's because I had this thing moved around. There you go. Let's see that thing. There we go. There's the conical helix, all centered on which axis? The z-axis. Cool, so I'll close this out. The next one I don't have to put on here, but I was going to help me predict this next one. So hit the lights. How about this? Sine of t, cosine, and you know this could have a sine of 4t, and this could be cosine of 4t. And you all agree you still have the relationship, x and y is forming a circle? Put a 4 here. So let's think about that. Before I had a t here, it allowed it to what? Keep what? Growing and growing and growing. But in this case, z is always going to be a 4. So what should happen here? We still got that circle relationship down here going on, but z is always 4. So what should happen? Up at z equal to 4, we'll just have a circle. It'll just keep going around and around and around, repeating the path. In the plane, z equals 4. It'll just be a circle path. Cool? It'll just keep repeating that. Because z will always remain what? 4. There's no t to let it what? Increase. And by the way, the radius here wouldn't be 4. The radius is still 1. Because sine of this squared plus cosine of this squared, right, would still be equal to 1. Increase the radius, I'd have to put numbers in front of it. So far, so good? Okay, and one more. What if I got sine of t, I got cosine of t, then you got sine of t. Now everyone, this doesn't have to be a perfect sketch, but we got to get a sense of what's going to go on here. Now all three have trig functions. Well, let me hide this. Can you first tell me about x and y again? What's the relationship? Between x and y, don't you have a circle again?
Mm-hmm.
All right. Traveling in this circle pattern between x and y like this. But then this z component is now a trig function. Trig functions are periodic, aren't they? So while this thing is doing that, what I'm saying is this, ready? X squared plus y squared does equal 1 in this problem. Do you all agree?
Mm-hmm.
Always. So this travels on a cylinder, is what we're saying. This curve must travel on a circular cylinder. This graph right here, it's a function, but it must travel on the surface of a circular cylinder. That must happen. We see that relationship. But as it travels on the circular cylinder, different from the others, it's not going to do the what? That circular helix, that was traveling on the surface of a cylinder, right? This is going to make it periodic. So what it's going to do on the surface of that cylinder, just think it's a trash can. It's just going to keep repeating the same pattern like this, going around the pattern. It's going to look something like this. You know, and just keep going up and down on the surface of that circular cylinder. I mean, there's my sketch. But did you want to see it with the software? Let's just see how it looks. Like, well, that's what's going to happen. Because it'll just keep, this is periodic. It keeps repeating, true? As it sits on this what? The surface of a circular cylinder, and it'll just keep repeating that same pattern. And you go, well, let's look at it. Let's just see how that would look. So I'll type this in. What was it? Let's see. Three-dimensional. I'm going to do parametric. How does this look? All right. Sine of t. Y is what? Cosine of t. And z is sine of 2 times t. I'll add a few more t values. Make it increase to like t equals 50. Divisions. How about 150? Let's just see how this comes out. There we go. I'm going to view the axes. All right, let's just get over here. There it goes. It just keeps repeating that pattern. Isn't that cool? This is really sitting on the surface of a cylinder. If I tip it upside down, maybe you can see it. It's like, oh yeah, it's just on the surface of a cylinder. That's the cool thing about this. You can twist it and turn it. But that's what's happening there. And that's why I did this, just to give you a sense of that. Cool. When it comes to rough sketch, you can sketch something like this, but sometimes I like to just have you do a matching. Cool. Ready? Wait, helix. What else was there? There was the conical helix. Just a circle. And then maybe something like this that's just traveling on a circular cylinder, but it's a vector curve that just keeps repeating the same pattern. That involves trig functions like that. And again, everyone, I just want to point out, if you go, well, how do I sketch something different? Like t squared, t cubed. Oh, we don't have to do that now. Now you're just plotting points. You're plotting points that see how that thing, and it'll just skyrocket off. Because as you can tell, as t increases, all these what? Keep increasing. Cool. Awesome. So that's vector curves. Those are the main ones to know. You know how to plot them in two-dimensional space and three-dimensional space. You know how to make the vectors. That's awesome. There's a couple problems in this section I want to work with you before we really just focus on the derivatives and the integrals. So this is number 29 on page. Well, I'll just put the section number in section 13.1, and this is what it asks you. So now they just have questions. At what point does the curve. All right, here comes my vector curve. R of t, and they love to use R, you can use different letter, equal to t, so I, there's the x component, plus 2t minus t squared k. All right. At what point does that curve intersect the parabola? Z equal to x squared plus y squared. Okay. So we're going to brainstorm how to handle this problem. One of the common themes in Calc 3. X's, Y's, Z's, but now we have this parameter what? T, and we got to make that connection. Before we made a table. You saw the relationship we talked about in those vector curves. Oh, that must be traveling on a cylinder. How the heck are we going to do this? Now I see this word intersect, but we know in all mathematics, when it comes to intersect, don't we do some kind of substitution? So that's what we know. Maybe you got stuck on a test. You're like, wait, somewhere, somehow, I have to substitute something. Any suggestions? Someone will come up with this. Somehow, if we can do a substitution, we can find the exact point that's on this curve that it intersects then. It's like, well, what's hidden is, what letter is this?
X.
That's the x component. X is equal to what?
One.
T. What's weird is, what's y? 0.
Zero.
You all notice that? They got it in standard basis form. You might wanna, you don't have to, but you might prefer to write in this format. There's x, it's a t. What's the y? It's a 0, and what's the z? What I got enough room there? 2t minus t squared. Alright, but that's z. Z is 2t minus t squared. Y is 0. X is t. And what can I do with these? Substitute them here. We can solve for what letter? T. Let's do it. What goes here? 2t minus t squared. I'll substitute that for the z. Equals x squared, t squared, plus
0.
0 squared. All right, how do you solve that? 2t minus t squared equals t squared. Well, I can subtract the t squared from this side, right? 2t minus 2t squared equals 0. Factor. Let's factor rather than divide things on both sides. When you divide variables in math, in an equation, you sometimes lose a point. So let's factor. So I factor out a 2t, what are you left with? 1 minus, whoops, 1 minus just a t? Is that right? So what's the 2t values? 2t equals 0, you get 1 minus t equals 0, you get t equal to what? Great job. Now, did I answer the question? Almost. Just we're 99% there. Point. So let's write these as points. What's going on? T equal to 0. Can we use this? There it is. It's got to be on that vector curve. Plug in t equal to 0. What's the point? 0, 0. What's 0 minus 0?
0.
All right, there's 1 point. What's the other point?
1.
1, 0. What's 2 times 1 minus 1?
1.
There's the 2 points. At those 2 points, you got this funny curve going right through that paraboloid. Remember the paraboloids like the windsocks? Centered on the z-axis, right? And somewhere that curve just went kind of boom, boom. Just hit through, and then we're talking about it actually intersected the surface. It intersected the surface of it at this point. And now here's another one. This is number, still in 13.1, it's number 48 in the textbook. You will see these in the practice set. You'll see problems like this in the practice set. Okay. And you can do 2 vector curves. 2 particles travel along space curves. So I'll start with that. Two particles travel along space curves. Period. And I'll give you the two space curves. Space curves, vector functions, right? What are they? One of them is r of t equal to t squared t cubed. Other one is rt equal to 1 plus 2t. 1 plus 6t and 1 plus 14t. Alright. Hey, to distinguish between these two vector curves, they put subscripts of 1 here and a subscript of 2 there. There's the two vector curves. And I'll put the question down in a second. This problem has two questions. Alright? It's about collision and intersection. Alright? They asked, do the particles collide? And secondly, they asked, do the particles intersect? Alright. So, do the particles collide? Question mark. Do the particles intersect? Travel along these space curves. We got to take each one of these separately, alright? That's our question. Oh, I'll go on there with wind plot and sketch it. Nah. We'll get this algebraically. This is r sub 1, this is r sub 2, these are the two vector curves. Let's start with collision. For collision, that means it's going to hit the same point, we know that, at the same time. Think of t as time. Think of t as time. So what's got to happen for collision? Here they are traveling 1 second, 2 seconds, 3 seconds, 4. Same point at the same time these two particles will collide. So what's intersect? The paths intersect? Oh yeah. They go through the same point, but they could be what? Different times. Does that make sense? Different t-values. Hit the same point at different t-values. They're just traveling the path. This touched that point at t equal to 1. The other one touched it when it was at t equal to 10 or t equal to 12 or something. So I'll just say what? Same point, but it could be different. Since it's t, we'll just say t values, right? Alright. Let's do each one separately. Let's start with collision. Then we'll do this one. So start here. So I'm going to erase this so you don't think I'm doing this with intersection. Let's see. Do the particles collide? What's the algebraic approach to determine that? Be the same point at the same time. You agree I can set this equal to this? I love it. So let's do that. I mean, I could have done this equal to that, but that looked more complicated. So I'm thinking, okay, then you're going to have to equal this. And the question is, do they collide? This might be an answer of no. We'll find out. So I'm going to let t would have to equal 1 plus 2t. If it's got to see the same point at the same time, I'll set those two x's equal to each other. Now I can solve for what? So I subtract the t on both sides. I get negative t equals 1, so t equals 2. Negative 1, right? Do they collide? I'm not sure yet. I only checked the what? The x components seem to match up. For these to collide, I now have to take this number right here, plug it back into all three of these, and plug it back into all three of these. And as long as those three numbers match these three numbers, then the answer is yes. If they don't, the game's over. The answer is no to this question. Okay? Now, we already know these are going to be equal, right? But we have to check these and these just at that number. That's all we got to do. Let's do it. So keep an arrow. Let's check. What would be the point over here?
Negative 1 squared.
So negative 1 for that. This would be just what, a 1?
Yeah.
What would this be?
Negative 1.
All right, this would have to match. Negative 1, okay, it's looking good so far. What's 1 plus 6 times negative 1?
Negative 5.
Game's over. I'm not even checking this. Here. Who cares? It's over. What's the answer? The answer is no. Do the particles collide? No. There's our justification. These would have to be equal. All right, corresponding components would have to be equal. We saw for the t value, would have to match in the other place. So we're sure it doesn't happen. I only started with that because that was the simplest of them all. All right. Now for they didn't collide, maybe they'll intersect. So now, can I go on to intersect? Different algebraic approach. Very similar, but different. Do the paths intersect? That's the same point, perhaps different times. Because of this, here's my major recommendation. Would you please, let's go into one of these two and change the parameter letter. Leave one of them t's, but make the other one a different parameter letter. That's going to allow us to see whether or not they intersect. So I'll leave that one in t's. I wonder if I use m here. So this is what I'm going to do for intersect. I'm going to go over to this one and just, rather than t, I'm going to use m. Think of this as r of m. Because if not, we'd be lost trying to see whether or not these are different points, different times. All right, intersect. So there's my first recommendation for intersect. Change one of them to a different parameter letter. M. I would use s, but s looks like a 5. All right, and you know what to do. What has to be equal?
T is equals to 1
It's got to
plus
be intersect. The paths intersect. Well, t would have to equal to 1 plus 2m. But you understand something? I've got two different letters in that equation, right?
Yeah.
So let's set up another equation. What else would have to be true? I'll put the word in. T squared would have to equal to
1 plus.
I'll step away. You know how to solve a system of equations?
Uh-huh.
That's what we got to do. Let's solve that system, see what we get, then we'll check them. If they come out all right, I'm going to find that these two paths do intersect. All right. How do you do substitution? I got to solve this system.
So 1 plus 2m whole square equals.
So you're saying take this, substitute it into the t,
Uh-huh.
okay? Solve this system of equations. Okay. Great idea. I got to FOIL that. 4m squared plus 4m plus 1. 1 plus 6m. You know how to deal with quadratics. I'm going to set it all equal to 0, right? And then factor. So I'm going to subtract 6m and subtract 1 from both sides. I get 4m squared minus 2m equals 0. Let's factor. What can I factor out? 2m. And then what do you have?
2m minus 1.
The two values of m are m equal to 0
and half.
and m equal to half. Hey, do you do me a favor? Right underneath these, could you write down the corresponding t values that go with both of these? I'll use a different color chalk. What's the t value that goes with m equals 0? And you look, you go, where do I look? You could use this right here if you want, or you could use this one. At m equal to 0, what's t equal to?
1.
Right there. He's got to be, and then at m equal to a half, what's t equal to at m equal to a half?
2. 2.
T equals 1 plus 2 times 1 half, 1 plus 1, 2.
Yeah.
Cool? But it appears that when we can check, it does intersect. We're getting these two solutions here, and we'll just check the points. What's going on at m equal to 0? And what's going on at t equal to 1? What's the 1 point? All right, let's plug 0 in there. What do you get?
0. Oh,
0? Oh wait,
That's
that's
a-
t's. My bad. When I got to plug, that's t. So I got to plug in a 1 in here. What do I get? 1, 1, 1. Let's double check. I want just to make sure we did this. Plug in a 0 into these m's, we should get the same point.
1, 1, 1.
1 plus 0, 1 plus 0, 1 plus 0 is 1, 1, 1. That's one of the points. So these paths do intersect. This is one of the points. What's the other point? The other point is when m equal to a half, when t equals 2. Let's check it. Plug in the t equals 2 in there.
2,
2,
4, 8.
4, 8. Let's just make sure. You know, we're just checking our work. Let's just check to see if we did this right. Plug in a half into m, make sure you get the same point. 1 plus 2 times a half,
1 plus
that
2.
gives you 2, right?
Uh-huh.
1 plus 6 times a half, 1 plus 3, 4.
4.
And 1 plus 14 times 1 half, 1 plus 7 is 8.
Right.
There. These are the 2 points. There were 2 points where the paths intersect, but did these two paths collide?
No.
No. Kind of like when you watch all those planes and the different paths are taken, and then they tell you about that one day, whoa, there was a close call. It's like, the paths intersected, but they did not collide, correct? Cool, space curves. Hey, can I erase those? Nice. Hey, the rest of the stuff is 13-2. So we're just gonna deal with tangent vectors, velocity vectors, and all that stuff. We don't have to do any more sketches though. We did that one sketch. Everyone knows how to sketch a tangent vector, right? It's always tangent to the curve or an acceleration vector. Sometimes it's pointed inward, it's traveling